In this video, we're going to discuss function composition, how it's defined, evaluate a function to get a number, and then come up with a new rule for function composition. So what is function composition? Say you're given two different functions. We call those functions f and g of x. Then the following applies. We get the circle that symbolizes function composition. It looks like it might be a multiplication dot, but it is not. We are not multiplying here. This is equivalent to the following statement here, that we're going to take one function and plug it into the variable of a second function. So we would take the g function, plug it into the f function. The way we pronounce this is f of g of x, or sometimes you may hear f composed with g, but most of the time you will pronounce it f of g of x. And we could switch the letters around and end up calling it g of f of x. Sometimes people refer to this as fog and golf. So that's what function composition is. And a lot of textbooks will use an illustration of mappings to show how function composition works. First, say we have the domain of g. Remember, domain is your x values. What are the numbers that you're going to be plugging in? So we take some type of number that's in our domain, and we plug it into the g function. We evaluate it. When you plug it in, you get an output, your g of x output. That is some number. But when your outputs are put into a function, we call that the range of g. But the range of g ends up turning into the domain of the f function. So we take the g function, we plug it into f. It spits out an answer, and we call that f of g of x. So that would be called the range of f. And all of this just to show you that when you plug x in from the domain of g, you're able to map that number to the output, the f of g of x, the range of f. That is called f of g of x, or f composed with g. Now, for those of you in Algebra 2 right now, this mapping may not make a whole lot of sense, so let's try to do some examples and show you how this works. So we have some functions here. F of x is going to be x squared minus 4. G of x is going to be 2x plus 1, and we want to find the following values. Well, let's start with f of g of 3. Using what our rule says, is that f of g of 3 is written like this. And we're going to start inside out. Okay, we need to know what g of 3 is before we can even figure out what it is when you put it into f. So I go through and ask myself, what is g of 3? I look at my g function. It's 2x plus 1, so I leave the open parentheses there so I know what I'm plugging in. Plug in the 3, do my order of operations. 2 times 3 plus 1 is going to give me an output of 7. What I then do with this 7 is I'm going to now plug it into the f function. So I need to know what f of 7 is. I leave my parentheses where the x is at, so I know to plug my 7 in. 7 squared minus 4, 49 minus 4 is 45. There is the answer. So what is f of g of 3? F of g of 3 is equal to 45. So the next question is, can we do this backwards? Can we do g of f of 3 and get the same answer? Let's see what we can do. Okay, so let's change the order. Put the g function first, the f function second. Go through what function composition is. We're going to take the f of 3 output and we're going to plug it into the g function. So this time, I need to know what is f of 3 first. Plug 3 into the f function. Remember, that was x squared minus 4. So we put 3 in. 3 squared minus 4 is going to give us an output of 5. So we take the output 5 now, much like the 7 that we had in the previous example, and we're going to now plug it into the g function. What is g of 5? Well, we have our g function that was 2x plus 1, so we get to put a 5 where the x is at. Go through the order of operations. 2 times 5 plus 1 gives us an output of 10. So f of g of 3 was 45, but g of f of 3 gives us an output of 11. So those numbers are very different. So what this tells us is that f of g of 3 does not equal g of f of 3. In other words, order matters, and function composition is not commutative like addition and multiplication. Remember the commutative property that the order did not matter. 2 times 3 is 3 times 2. 2 plus 3 is 3 plus 2. It doesn't work the same way with function composition, so you have to be very, very careful in how you do your order for function composition. So that's how you evaluate with numbers. We can do the same thing to write a new rule for the function. So if you don't see a number that you want to plug in for x, your answer will not be a number here. So we're going to go through and find f of g of x and g of f of x if they exist for the following two functions. F of x is going to be 2x minus 5. G of x is going to be 4x. Let's start with f of g of x. Again, just like with the numbers, I am going to work inside out. F of g of x would be the same as me saying, what is f of 4x? Because 4x is the g function. Wherever I see an x in the f function, I will replace it with a 4x. So there's the original f function, 2x minus 5 with the parentheses. That blank parenthesis I fill with the 4x. Whatever order of operations pop up, I simplify. The only thing I can simplify here is 2 times 4x, and that will give me an answer of 8x minus 5. So that's f of g of x. What is g of f of x? Well, the f of x function is 2x minus 5, so we're going to be plugging 2x minus 5 into the g function wherever the x is at. So the g function is 4x, so the x gets replaced with the 2x minus 5. Here you see that we're going to be distributing the 4 through the parentheses, and its output is 8x minus 20. Notice again, the outputs here are different. 8x minus 5 is a little bit different than 8x minus 20. So once again, the order does matter with f of g of x compared to g of f of x. Of course, these problems do get a little bit more complicated, especially when you throw exponents into the problem. So let's look at an example that involves some exponents. Now we got the f of x function is x squared plus 2. G of x is x minus 6. Starting with f of g of x. The g function is x minus 6. So anywhere there's an x in the f function, x minus 6 gets replaced. So there's the f function without the x. We know that we're putting x minus 6 inside the parentheses. And be careful here. We are not distributing the 2 through the parentheses because we have a difference between the terms. What is the second power telling us to do? We're doing the base times itself twice, so we will have to FOIL out the x minus 6. When you FOIL, you get the following statement, x squared minus 6x plus 36. But at the same time, at the end of the problem, there was plus 2. This is expanded, so we combine any of our like terms. There are like terms with the negative 6x's, and the 36 and the 2. So the answer here for f of g of x would be x squared minus 12x plus 38. Let's go in the other direction. Let's do g of f of x. So the f of x function, it's x squared plus 2. So we're plugging x squared plus 2 into the x of the g function. What is the g function? It was x minus 6. So in that parenthesis there, all I'm plugging in is the x squared plus 2. And this one is a much faster problem. The only like terms that we have here are the plus 2 and the minus 6. So the answer of g of f of x is x squared minus 4. And there you have it. That is function composition with evaluated numbers, and function composition to write a new rule by plugging one function into the other.